In the days before calculators, if you wanted to multiply a series of numbers, there was two ways to do it. You could multiply each number by the next in a series of binary multiplication operations, or you could take the logarithm of each number and add them. Then take the antilog of the sum of the logarithms to get the answer. This was much more efficient than multiplication. In multiplying the series of numbers, you would have over 30 operations just to multiply the first two numbers. Using logarithms, it would take about that many to complete the entire operation. Symmetrical components uses the same analysis concept. Given a set of unbalanced phasors, you can perform a multi-phase network analysis and come up with a network solution. Or you can transform the unbalanced phasors into a system of balanced phasors, then do a single-phase network analysis to get a symmetrical component solution. Then transform it back into the network solution. Solving a network involves finding all the node voltages and all the branch currents in the network. In this day of modern computer systems, why do we study symmetrical components? We progress by evolution instead of revolution because the future is inextricably bound to the past. Large databases for power systems are maintained in the form of symmetrical components. All computer programs are based on assumptions and require input parameters. You need to know how to evaluate these assumptions and parameters. Most computer systems for power systems are based on symmetrical components. Most technical papers assume a knowledge of symmetrical components. They are used for hand calculations, and you need to know when your computer is wrong. These are the topics that we are going to cover in this video. We are going to do a quick review of trigonometry, vectors and complex numbers. We are going to define phasors and symmetrical components and explore three-phase network connections. We are also going to review network theorems and talk about sequence networks. Finally, we are going to apply these to solving faulted three-phase systems. In the review of trigonometry, we will cover the following: the sine function, the cosine function, the tangent function, the arctangent function, and the unit circle. What is the sine of an angle theta? It is a number between -1 and 1, inclusive. This number represents the ratio of two sides of a right triangle, namely side B divided by side C. If the length of side C is equal to 1, then the number, sine of theta, is the length of side B. Whenever you see the symbol sine of theta, you should think, number. What is the cosine of an angle theta? It is a number between -1 and 1, inclusive. This number represents the ratio of two sides of a right triangle, namely side A divided by side C. If the length of side C is equal to 1, then the number, cosine of theta, is the length of side B. Whenever you see the symbol cosine of theta, you should think, number. What is the tangent of an angle theta? It is a number between -infinity and infinity. Again, this number represents the ratio of two sides of a right triangle, namely side B divided by side A. The number, tangent of theta, is the slope of the line C. What is the arctangent or inverse tangent of angle theta? It is an angle between 0 and 360 degrees or an integer multiple thereof. When you see the symbol for inverse sine, cosine or tangent, you should think angle. Now, if we let theta vary and keep the length of C constant, the ordered pair A, B will trace out a circle in the xy plane. Since the equation of a circle is r squared equals x squared plus y squared, when r is held constant, this implies that c squared equals a squared plus b squared. The Pythagorean theorem traces a circle when c is held constant. If c equals 1, then a equals cosine theta and b equals sine theta. Therefore cosine squared plus sine squared equals 1 is a circle with radius 1, a unit circle. So now we can describe a right triangle in a plane by an ordered pair of numbers, a, b. From this ordered pair, the rectangular components of C, we can determine the magnitude, that is the length of C, the distance from the origin to the point AB. And we can determine the angle theta that C makes with the x-axis. This is the arctangent of side B divided by side A. Next we are going to cover rectangular and polar forms of vectors, and how we add and multiply vector. Now we can view the ordered pair, AB, as a two-dimensional vector. We can describe a vector in two different ways. First by the rectangular components, A and B. Or secondly we can describe it by its magnitude r, C of the triangle, and its direction, angle theta. The first description is called the rectangular form and the second is called the polar form. To convert from the rectangular form to the polar form, to find the magnitude, r squared equals a squared plus b squared. The angle theta equals the arctangent of b divided by a. To convert from the polar form to the rectangular form, a equals r cosine theta, b equals r sine theta. Again, if r equals 1, a unit vector, then a equals cosine theta, and b equals sine theta. Given two vectors, AB, and DE, how do we add them? We add vectors graphically by placing the tail of one vector to the head of the other vector. The sum of the vectors is called the resultant. Computationally you add the vector rectangular components, component by component. That is, the resultant becomes a plus d and b plus e. Next we are going to discuss complex numbers. We are going to answer the following questions. What is a complex number? How do we add complex numbers? How do we multiply complex numbers? And what is the complex conjugate? Complex numbers are simply ordered pairs. The sum of two complex numbers, the pair a, b, and the pair d, e, is defined as a, b, plus d, e, equals a plus d, b plus e. This is the same as vector addition. The product of two complex numbers, ordered pairs a, b, and ordered pairs d, e, is defined as a, b, times d, e, equals the ordered pair a times d, minus b times e, and a times e, plus b times d. This is the same as polynomial multiplication. Note that this is not the same as the dot product or the cross product. For the further definition of complex numbers, after some mathematical manipulation, we come up with the need to solve equations of the form x squared plus 1 equals 0, or equivalently x squared equals minus 1. This equation has no solutions in the real number domain. So we define j equals the square root of minus 1. We will also denote the ordered pair a, b, as a plus jb to remind us of the vector addition properties of complex numbers. The product of two complex numbers, ordered pairs a, b, and ordered pairs d, e, is defined as a, b, times d, e, equals the ordered pair ad minus b, and a plus bd. This is the same as polynomial multiplication. The multiplication and division of complex numbers using the rectangular form is often cumbersome. Often it is easier to use the polar form. For multiplication, multiply the magnitudes and add the angles. For division, divide the magnitudes and subtract the angles. Since the xy plane describes the domain of real numbers, and our equations have few solutions in this domain, we must use a plane that describes the complex number domain. The horizontal axis of this plane is the real axis and the vertical axis is the imaginary j-axis. Suppose we have two vectors represented by a, b, and d, e, or equivalently r1 angle theta, magnitude 1.5 at 30 degrees, and r2 angle phi, magnitude 2 at 45 degrees. We could multiply the vectors component by component. Or we could use the much easier polar form. As seen in the graph, multiplying complex numbers effectively scales r1 by r2 and rotates the direction of r1 by the angle phi. This gives us a vector of magnitude 3 at 75 degrees. Multiplying the vector r1 by the unit vector simply rotates the vector r1 through the angle of the unit vector. Multiplied by a unit vector, 1 at 30 degrees simply rotates r1 by 30 degrees for a vector of 2 at 75 degrees. Simply changes the direction of r1. The conjugate of a complex number, a plus jb, is a minus jb. To form the conjugate, simply change the sign of the imaginary part of the complex number. Changing the sign of the imaginary part changes the sign of the angle. Given a vector 2 at 45 degrees, its conjugate is a vector 2 at minus 45 degrees. Or equivalently 2 at 315 degrees. 360 degrees minus 45 degrees. Angular velocity, omega, is a measure of how fast something is spinning. It is measured in degree per second, radian per second, revolutions per minute, etc. The greater omega, the faster the object spins. Therefore, if the angular velocity is omega, then the angle theta at time t is omega t. The point here is that omega t denotes a constantly changing angle. In this section we are going to discuss phasors. We are going to give a mathematical description of phasors. We are going to discuss them as rotating vectors. And then we are going to view them from a rotating coordinate system. Suppose that we have a unit vector r1, rotating at a constant angular velocity omega. How do we describe r1 mathematically? Since r1 is a unit vector, r1 equals cosine theta plus j sine theta. Theta is a constantly changing angle, omega t. Substituting omega t in the above equation for theta, we get a rotating unit vector, r1 equals cosine omega t plus j sine omega t. Now let us examine the rotating unit vector at time t equals 0. r1 equals cosine omega t plus j sine omega t. Since t equals 0, omega t is also equal to 0. r1 angle 0 equals cosine 0 plus j sine 0. r1 angle 0 equals 1 angle 0. At time 0 the unit vector is aligned with the real axis. Now suppose we have a rotating unit vector r2, rotating at the same speed as r1. However, at time 0 the angle of r2 is phi. How do we describe r2 mathematically? Since a unit vector is r2 equals cosine theta plus j sine theta, a rotating unit vector is r2 equals cosine omega t plus phi plus j sine omega t plus phi. Let us examine the unit vector r2 at time 0. r2 equals cosine 0 plus phi plus j sine 0 plus phi. r2 equals cosine phi plus j sine phi. We see that r2 makes an angle of phi with the real axis at time 0. Remember, r1 and r2 are spinning at the same speed, so angle phi between them will remain constant. Also, the magnitude of the sums, differences, products and quotients of r1 and r2 will remain constant. The angles of the sums, differences, products and quotients of r1 and r2 will rotate at a speed of omega. Since I am easily confused, and all this rotation is confusing me, I am going to stand at the origin of the graph and rotate with the vectors. What do I see? All the vectors become stationary with respect to me. In other words, I am viewing the vectors from a rotating frame of reference. i.e. a rotating coordinate system. This transforms the rotating vectors into stationary vectors. Mathematically, R2 equals cosine omega t plus phi plus j sine omega t plus phi becomes R2 equals cosine phi plus j sine phi. So now we have come full circle to where we were 4 slides ago. Why did we go through this last exercise? To emphasize that phasors are representations of time-varying sinusoids of voltages and currents. Phasors greatly simplify calculations of time-varying sinusoidal quantities. In summary, phasors are rotating vectors characterized by sinusoidal varying complex numbers. By choosing the proper coordinate system, we can treat them as stationary vectors. We add complex numbers by adding their components vectorially. We multiply complex numbers by multiplying their magnitudes and adding their angles. Multiplying a phasor by a unit phasor rotates it by the angle of the unit phasor. We now have the tools to tackle symmetrical components. In this section we are going to define and describe symmetrical components. Define the A operator. Define sequences. Apply symmetrical components to sequences. And apply symmetrical components to unbalanced phasor sequences. Symmetrical components are a mathematical transformation that changes a system of polyphase unbalanced phasors into a system of balanced phasors. The number of components of the symmetrical system is equal to the number of phases in the original system. A three-phase system decomposes into a system of 3 symmetrical components, each having 3 balanced phasors. We call these the positive, negative, and zero sequences. Suppose that we define a unit phasor as such that A equals 1 at 120 degrees. Suppose also that we have an arbitrary phasor R1 at angle phi degrees. If we multiply R1 by A, R1 at angle phi equals R1 at angle phi plus 120 degrees. This shifts R1 by 120 degrees. A squared times R1 at angle phi equals R1 at angle phi plus 240 degrees. This shifts R1 by 240 degrees. A cubed times R1 at angle phi equals R1 at angle phi plus 360 degrees equals R1 at angle phi. This shifts R1 by 360 degrees, bringing R1 back to its original position. If we shift the phasor by A squared, it rotates the phasor counterclockwise, that is the positive direction, by 240 degrees. If we shift the phasor by A to the negative first power, it rotates the phasor in the clockwise direction, i.e. the negative directions, by 120 degrees. This puts the phasor in the same position as above, so that a squared is equal to a to the negative 1. Since a cubed rotate the phasor by 360 degrees to its original position, then a cubed equals 1. Since the conjugate of a is the negative of its angle, a conjugate is equals to a to the negative 1. It is also equals to a squared. If you add three vectors a 120 degrees apart, they add up to 0, so 1 plus a squared is equals to 0. On the drawing, if you subtract a from a squared, tip to tip, you get a vertical line. The magnitude of the line is the square root of 3 and the vector points in the negative j direction, j square root 3. If you assume a set of vectors that are rotating counterclockwise, positive direction, the phasors pass the real axis in the sequence ABC, positive sequence rotation. If you assume another set of vectors, with the positions of the B and C phasors switched or rotating counterclockwise, the positive direction, the phasors pass the real axis in the sequence ACB, the negative sequence rotation. If an induction motor terminals are hooked up in the ABC sequence, the motor will rotate in one direction. If two of the leads are reversed, hooking the motor up in ACB sequence, the motor will rotate in the opposite direction. Suppose now that we have a balanced system of three vectors VA, VB, and VC. The magnitude of all three vectors is the same, say V. The three vectors are spaced 120 degrees apart as shown. Therefore, using VA as the reference vector, VA equals V at 0 degrees. VB equals V at 240 degrees. VC equals V at 120 degrees. Suppose now that we define three equations. 1. V0 equals 1/3 VA plus VB plus VC. 2. V1 equals 1/3 VA plus A times VB plus A squared times VC. 3. V2 equals 1/3 VA plus A squared times VB plus A times VC. Performing the operations of equation 2 on the positive sequence. V1 equals 1/3 VA plus A times VB plus A squared times VC. We rotate VB counterclockwise 120 degrees. A times VB equals V at 0 degrees. We rotate VC counterclockwise 240 degrees. A squared times VC equals V at 0 degrees. And VA equals V at 0 degrees. Summing 3V1 equals 3 times V at 0 degrees. Dividing by 3, we get V1 equals V at 0 degrees, the positive sequence voltage. Performing the operations of equation 3 on the positive sequence. V2 equals 1/3 VA plus A squared times VB plus A times VC. We rotate VB counterclockwise 240 degrees. A squared times VB equals V at 120 degrees. We rotate VC counterclockwise 120 degrees. A times VC equals V at 240 degrees. And VA equals V at 0 degrees. Notice that VB and VC have interchanged positions. Summing the three vectors, we get V2 equals 0. The negative sequence voltage. Likewise, applying equation 1 to the original vectors, V0 equals 1/3 VA plus VB plus VC. V0 equals 0, the zero sequence voltage. Now applying equations 1, 2, and 3 to the original vectors two more times, using VB and VC respectively as the reference vectors, we have successfully converted them into a system of symmetrical components. However, we do not have to apply equations 1, 2, and 3 to the other two phases because we know the three phasor systems are balanced and 120 degrees apart. So what have we achieved so far? In this particular example, we have shown that the phase variables of a balanced three-phase system of phasors are the positive sequence components of the system. And for a balanced system excited by a balanced positive sequence, the negative sequence and zero sequence voltages and currents are zero. Now suppose we start out with another balanced three-phase system. In this negative sequence system, the vectors VB and VC are interchanged from the previous balanced system. If we apply equations 1, 2, and 3, we end up with the positive sequence voltage, V1 equals 0. The negative sequence voltage, V2 equals V, at 0 degrees, and the zero sequence voltage, V0 equals 0. Again, for a balanced system excited by a balanced negative sequence, the positive sequence and zero sequence voltages and currents are 0. We call V1 the positive sequence component, V2 the negative sequence component, V0 the zero sequence component. Now suppose we have the case of three unbalanced phasors. VA equals 1 at 10 degrees. VB equals 0.5 at 235 degrees. VC equals 1.5 at 135 degrees. Applying equation 2, that rotates phasors VB by 120 degrees and VC by 240 degrees. Summing the rotated vectors give 3V1. Dividing 3V1 by 3 and showing the other two phases gives us our balanced positive sequence component. Now using the same three unbalanced phasors, VA equals 1 at 10 degrees, VB equals 0.5 at 235 degrees, and VC equals 1.5 at 135 degrees. Applying equation 3 that rotates phasors VB by 240 degrees and VC by 120 degrees. Summing the rotated vectors gives 3v2. Dividing 3v2 by 3 and showing the other two phases gives us our balanced negative sequence component. Going back to our original phasors and applying equation 1. Summing the vectors, we get 3v0. Dividing by 3, we get v0. Next we are going to cover network connections. The types we are going to cover are the ungrounded Wye, the impedance grounded Wye, the solidly grounded Wye, the ungrounded Delta, and the grounded Delta. There are other types of specialty connections such as the zigzag, Scott-T, etc. We will not be covering them. In an ungrounded Wye, equipment is connected with one lead connected to the phase and the other lead connected to a common point, usually called the neutral. There is no connection from the neutral to the ground. If the equipment is a load, then there is no ground path back to the source. There can be a voltage between neutral and ground in unbalanced systems. The impedance grounded Wye is connected like the ungrounded Wye, except the neutral is connected to the ground through an impedance. There can be a voltage between neutral and ground in unbalanced systems. During a fault, the neutral impedance limits the fault current. In the solidly grounded Wye, the neutral is connected to the ground with no intentional impedance. In a solidly grounded system, there is no intentional voltage between neutral and ground. In an ungrounded delta system, the equipment is connected with the leads across the phases. There is no neutral in an ungrounded delta system. In the grounded delta system, one of the phases is grounded. In some cases such as delta-connected transformers, the center tap of one the windings may be grounded. The grounding configuration greatly affects the zero sequence current. Suppose we have the network shown, and we apply positive sequence voltages to the three phases. Voltages of equal magnitudes spaced 120 degrees apart. What are the currents and voltages in the network? Using Kirchhoff's voltage law around three loops, the sum of the voltages around the green loop is minus Vc plus Ic times Z plus Ia plus Ib plus Ic times Zn equals 0. The sum of the voltages around the red loop is minus Vb plus I times Bz plus Ia plus Ib plus Ic times Zn equals 0. The sum of the voltages around the blue loop is minus Va plus Ia times Z plus Ia plus Ib plus Ic times Zn equals 0. Summing these three equations, 0 plus IA plus IB plus IC times Z plus 3 times IA plus IB plus IC times Zn equals 0. IA plus IB plus IC times Z plus 3 Zn equals 0. Since Z plus 3 times Zn does not equal 0, therefore, IA plus IB plus IC must equal 0. Vn equals IA plus IB plus IC times Zn equals 0. Therefore the neutral to ground voltage is 0 for a balanced system. IA equals VA minus Vn divided by Z equals VA divided by Z. IB equals VB minus Vn divided by Z equals VB divided by Z. IC equals VC minus Vn divided by Z equals VC divided by Z. The preceding calculations show that when a symmetrical three-phase Y network is excited by a balanced three-phase positive sequence voltage, only positive sequence currents flow, and the circuit can be analyzed on a single-phase basis. Since the three-phase source contains no negative sequence components, there are no negative sequence currents. This shows the positive sequence impedance is Z1 equals Z. Exciting the symmetrical network with a balanced three-phase negative sequence source, the negative sequence impedance will also be Z2 equals Z. And the currents will all be negative sequence. For passive circuit elements, non-rotating machinery, such as transformers, transmission lines, etc., the positive and negative sequence impedances are equal. Now suppose we excite the symmetrical network with zero sequence voltages, identical voltages on all phases, that is, the source voltages have the same magnitude and the same phase. What are the voltages and currents in the network? Since the voltages on all phases are the same, then the network can be redrawn as below. By Kirchhoff's law, V0 equals I times the quantity Z divided by 3 plus Zn. V0 equals I divided by 3 times Z plus 3 Zn. I0 equals I divided by 3. V0 equals I0 times Z plus 3 Zn. And Vn equals I0 times 3 Zn. The preceding calculations show that when a symmetrical three-phase Y network is excited by three single-phase zero-sequence voltages, that only zero-sequence currents flow, and the circuit can be analyzed on a single-phase basis. The zero-sequence impedance is Z0 equals Z plus 3 Zn. Now if we let Zn become 0, we have the solidly grounded case and Z0 equals Z. The neutral to ground voltage, Vn, is equal to 0. And if we let Zn become infinity, then we will have the ungrounded case and I0 equals 0, and the neutral to ground voltage, Vn, is equal to V0. For Zn between 0 and infinity, Vn equals V0 times 3 Zn divided by Z plus 3 Zn, is equal to 3 times V0, Zn divided by Z0. I0 equals V0 divided by Z plus 3Zn. We will now solve a problem of imbalanced ungrounded Y-connected network supplied with an unbalanced source using network analysis. Suppose we have an unbalanced voltage source VA equals 1.0 volts at 0 degrees. VB equals 0.5 volts at 240 degrees. VC equals 1.5 volts at 120 degrees. By Kirchhoff's current law, the sum of the currents at node N, IA plus IB plus IC equals IN is equal to 0. Substituting VA minus VN divided by ZA for IA and likewise for IB and IC, we get VA minus VN divided by ZA plus VB minus VN divided by ZB plus VC minus VN divided by ZC equals 0. Rearranging terms, we get VA divided by ZA plus VB divided by ZB plus VC divided by ZC is equal to VN times 1 divided by ZA plus 1 divided by ZB plus 1 divided by ZC. And we have a balanced network. Let ZA equals ZB equals ZC equals Z equals 1 ohm. Then, VA plus VB plus VC divided by Z equals 3Vn over Z. Eliminating Z from the previous equation, we get VA plus VB plus VC equals 3Vn. Entering our numerical values, 1.0 volts at 0 degrees plus 0.5 volts at 240 degrees plus 1.5 volts at 120 degrees equals 3Vn. Converting the phasors to rectangular form and solving for Vn, 1.0 plus J0 plus minus 0.25 minus J 0.43301 plus minus 0.75 plus J 1.299 equals 3Vn. Summing the terms and converting back to polar form, 0 plus J 0.866 equals 3Vn. 0.866 at 90 degree equals 3Vn. Vn equals 0.289 at 90 degrees. Calculating the branch currents, IA equals VA minus Vn divided by Z equals 1.0 at 0 degrees minus 0.289 at 90 degrees divided by 1 ohm. IB equals VB minus Vn divided by Z equals 0.5 at 240 degrees minus 0.289 at 90 degrees divided by 1 ohm. IC equals VC minus Vn divided by Z equals 1.5 at 120 degrees minus 0.289 at 90 degrees divided by 1 ohm. Doing the arithmetic, we get IA equals 1.04 at minus 16.1 degrees. IB equals 0.764 at 109 degrees. IC equals 1.26 at 126.6 degrees. Thus we have solved the network. We know all the currents and voltages in the network. Given the same symmetrical network, excited by the same unbalanced voltages. Let us now solve it using symmetrical components. VA equals 1.0 volts at 0 degrees. VB equals 0.5 volts at 240 degrees. VC equals 1.5 volts at 120 degrees. V1 equals 1/3 the quantity VA plus A times VB plus A squared times VC. V1 equals 1/3 of 1.0 volts at 0 degree plus 0.5 volts at 0 degree plus 1.5 volts at 0 degrees. Adding terms. V1 equals 1.0 volts at 0 degrees. V2 equals 1/3 VA plus A squared times VB plus A times VC. V2 equals 1/3 of 1.0 volts at 0 degree plus 0.5 volts at 120 degree plus 1.5 volts at 240 degree. V2 equals 0.289 at minus 90 degree. Continuing. V0 equals 1/3 the quantity VA plus VB plus VC. V0 equals 1/3 the quantity 1.0 volts at 0 degree plus 0.5 volts at 240 degree plus 1.5 volts at 120 degrees. Adding terms. V0 equals 0.289 at 90 degrees. I1 equals V1 divided by Z1 equals 1.0 volts at 0 degrees. I2 equals V2 divided by Z2 equals 0.289 at 90 degrees. I0 equals V0 divided by Z0 equals I0 divided by ZL plus 3Zn. Zn equals infinity, therefore I0 equals 0. From the fundamental equations, IA equals I1 plus I2 plus I0 is equal to 1 plus J0 plus 0 minus J0.289. Therefore, IA equals 1.04 at minus 16.1 degrees. IB equals A squared I1 plus AI2 plus I0 is equal to minus 0.5 minus J0.8660 plus 0.250 plus J0.1445. Therefore, IB equals 0.764 at 109.1 degrees. IC equals AI1 plus A squared I2 plus I0 is equal to minus 0.5 plus J0.866 plus minus 0.25 plus J0.1445. Therefore, IC equals 1.26 at 126.6 degrees. Thus we have solved the network. Next we will examine a delta-connected circuit. We excite a balanced, three-phase delta-connected load with a positive sequence source. At node A, IA equals IAB plus IAC. Substituting for IAB and IAC, IA equals VA minus VB divided by 3Z plus VA minus VC divided by 3Z. IA equals V at 0 degrees minus V at 120 degrees divided by 3Z plus V at 0 degrees minus V at 240 degrees, divided by 3Z. Summing terms. IA equals 3V at 0 degrees divided by 3Z. I1Z equals V1 since V is a positive sequence voltage source and IA equals I1. Therefore by definition Z equals Z1, the positive sequence impedance. The same also applies for the negative sequence impedance. Therefore the positive sequence network for the delta and Y network are the same. Consider the broken delta circuit shown consisting of 3 ideal voltage sources. Using Kirchhoff's voltage law, V equals VA plus VB plus VC. If VA, VB, and VC are 3 balanced voltages, then VA plus VB plus VC equals 0. So if we jumper across the terminals there will be no current flow. However, if the voltages are unbalanced using the fundamental equation for V0, a non-zero voltage V equals 3V0 will be developed across the terminals. Now let us close the delta with an impedance of 3Z. The current circulating in the delta circuit would be I equals V divided by 3Z is equal to the quantity VA plus VB plus VC divided by 3Z. I equals 3V0 divided by 3Z equals V0 divided by Z equals I0. V0 equals I0Z. If the voltage imbalance is too great, then the circulating currents can overheat transformers. Now let's redraw the previous circuit as shown. We distribute the impedance 3Z among the sources. ZA plus ZB plus ZC equals 3Z. Now assume the impedances are equal. ZA equals ZB equals ZC equals Z. By Kirchhoff's voltage law, the sum of voltages around any closed loop equals 0. So the sum of the line-to-line voltages VAB plus VBC plus VCA equals 0. Therefore the zero sequence voltage in the line-to-line voltages is 0. From the diagram, V AC equals versus A minus I0 times Z. V BA equals VB minus I0 times Z. V CB equals VC minus I0 times Z. From these equations, it can be seen that the zero sequence voltage in the line-to-line voltages is negated by the I0Z voltage drop of the circulating currents. Let's do an unbalanced delta-connected source example. Suppose we have an unbalanced voltage source. The phase voltages are VA equals 1.0 volts at 0 degrees. VB equals 0.5 volts at 240 degrees. VC equals 1.5 volts at 120 degrees. And we have a balanced network. Let ZA equals ZB equals ZC equals 1 plus J0 ohm. Converting the phase voltages to rectangular form. VA equals 1.0 plus J0. VB equals minus 0.25 minus J0.43301. VC equals minus 0.75 plus J1.299. The zero sequence voltage is 3V0 equals VA plus VB plus VC. 3V0 equals 1.0 volts at 0 degrees plus 0.5 volts at 240 degrees plus 1.5 volts at 120 degrees. V0 equals 0.289 at 90 degrees. The zero sequence current is I0 equals V0 divided by Z equals 0.289 at 90 degrees. Calculating the line-to-line voltages, VAB equals VA minus I0 times C equals 1.0 at 0 degrees minus 0.289 at 90 degrees. VBC equals VB minus I0 times C equals 0.5 at 240 degrees minus 0.289 at 90 degrees. VCA equals VB minus I0Z equals 0.5 at 240 degrees minus 0.289 at 90 degrees. VAB equals 1.041 at minus 16.12 degrees. VBC equals 0.764 at minus 109.1 degrees. VCA equals 1.258 at 126.6 degrees. Calculating the zero sequence voltage of the line-to-line voltages. 3V0 equals VAB plus VBC plus VCA equals 0. This shows the zero sequence of the line-to-line voltages is 0. Suppose we draw a closed surface around our delta-connected sources. According to Gauss's law, the sum of all currents entering a closed surface is equal to 0. This is a generalization of Kirchhoff's current law. Then, IA plus IB plus IC equals 0. Therefore no zero-sequence line currents exist in the delta-connected circuit. We have started with a point in a plane, taken it through vectors, complex numbers, phasors, and ended up with electrical networks decomposed into symmetrical component networks. We have come a long way. To convert to symmetrical component, V0 equals 1/3 times VA plus VB plus VC. V1 equals 1/3 times VA plus A times VB plus A squared times VC. V2 equals 1/3 times VA plus A squared times VB plus A times VC. To convert from symmetrical components, VA equals V1 plus V2 plus V0. VB equals A squared times V1 plus A times V2 plus V0. VC equals A times V1 plus A squared V2 plus V0. In networks with balanced network elements, positive sequence voltages produce only positive sequence currents. Negative sequence voltages produce only negative sequence currents. Zero sequence voltages produce only zero sequence currents. In passive networks, the negative sequence impedance is equal to the positive sequence impedance. In networks with unbalanced network elements, sequence voltages and currents interact. Positive sequence currents can cause negative and zero sequence voltages. Negative sequence currents can cause positive and zero sequence voltages. Zero sequence currents can cause positive and negative sequence voltages. There are no zero-sequence line currents in delta-connected networks. There are no zero-sequence voltages in the line-to-line voltages. Zero-sequence currents can appear as a circulating current in the delta. The voltage across the broken delta is 3 times the zero-sequence voltage. The positive sequence impedance is 1/3 of the phase impedance. The positive sequence impedance is equal to the phase impedance. The zero-sequence impedance is infinite for ungrounded Wye networks, therefore no zero-sequence current flows. For solidly grounded Wye networks, the zero-sequence impedance is equal to the phase impedance. For impedance-grounded systems, the zero-sequence impedance is the phase impedance plus 3 times the neutral impedance. For impedance-grounded systems, the neutral-to-ground voltage is 3I0Zn. This ends the review of symmetrical components. We will next discuss network theorems. Then apply symmetrical components and network theorems to calculating fault currents. The next section discusses network theorems. We will define the following and show the application of them. Series impedance, parallel impedance, Delta-Wye transform, Thevenin's theorem, Norton's theorem, and superposition. Elements are said to be in series when the same current flows through each of them. The total impedance is the sum of the series impedances. The total impedance, Zt, equals Z1 plus Z2. Elements are said to be in parallel when they have the same voltage across them. The total impedance is the reciprocal of the sum of the reciprocals. That is, the total admittance is sum of the admittances. The admittances are the reciprocals of the impedances. To find the total impedance, add up the admittances and take the reciprocal of the sum. For two elements in parallel, the total impedance is Z1 times Z2, divided by the sum of Z1 plus Z2. For elements of the same impedance in parallel, the total impedance is the impedance of a single element divided by the number of elements. Sometimes when reducing networks it becomes necessary to transform delta-connected subnetworks into Wye-connected subnetworks and vice versa. Using the formulas shown you can convert from a delta to a Wye. If the impedances are balanced, the ZAB equals 3ZA, and likewise for the other phases. The formulas shown are used to convert a Wye subnetwork into a delta subnetwork. Thevenin's theorem states, at any terminal pair the network can be replaced by an impedance in series with a voltage source. The voltage source is equal to the open circuit voltage at the terminal pair. The impedance is that impedance that is measured between the terminals with all independent sources removed. Voltage sources are shorted, current sources are open. Calculating the open circuit voltage VOC, using the voltage divider rule, VOC equals 1.0 volts, at 0 degrees times R2 divided by the quantity, R1 plus R2, times VOC, equals 0.5 volts. Shorting the voltage source and calculating R1 in parallel with R2, equals 0.5 ohm. The Thevenin equivalent circuit becomes as shown. The Thevenin equivalent impedance can also be calculated as the open circuit voltage divided by the short circuit current. The short circuit current, ISC, equals 1.0 volts, at 0 degrees divided by R1. ISC equals 1.0 volts, at 0 degrees divided by 1 R Thevenin equals 0.5 volts divided by 1 amp equals 0.50. Norton's theorem states, at any terminal pair the network can be replaced by an impedance in parallel with a current source. The current source is equal to the current that would flow through the shorted terminals. The impedance is the impedance that is measured between the terminals with all independent sources removed. Voltage sources are shorted, current sources are open. Shorting the terminal and using the current divider rule. I1 equals R2 divided by the quantity, R1 plus R2, times 1.0 volts, at 0 degrees. ISC equals 0.5 amp. Opening the current source puts R1 and R2 in series, so R equivalent equals 2 ohm. Superposition is the principle that the response of a linear system to excitations from multiple sources is the same as the sum of the responses of the linear system to the individual sources with all other independent sources removed. Voltage sources are shorted. Current sources are open. Given the circuit shown, excited by a voltage source and a current source, we will solve the circuit using superposition. Eliminating the current source, we get the first circuit. Reducing the circuit, combining the two 1 ohm resistors and the 2 ohm resistor, we get an equivalent resistance of 1 ohm as shown in the second circuit. Calculating the currents and voltages due to the voltage source, we get a source current of 0.5 amps with 0.5 volts. The currents in each branch are 0.25 amps. Eliminating the voltage source, we get the first circuit. Reducing the circuit, combining the parallel 1 ohm resistor and the 2 ohm resistor, we get an equivalent resistance of 2/3 ohm as shown in the second circuit. Calculating the currents using the current divider rule, we get 0.75 amps and 0.25 amps, with a source current of 1 amp. Calculating the voltage, we get 0.5 volts. Expanding the circuit, we get the branch currents and node voltages shown. Summing the currents in the branches and summing the voltages at the nodes, we have solved the circuit. The next section we will cover faults on three-phase systems. Most faults on three-phase systems result in unbalanced systems. The fault impedance may not be zero. If the fault impedance is zero, the fault is said to be bolted. The positive, negative, and zero sequence currents and voltages are not independent. We interconnect the sequence networks in particular ways to account for this interaction. There are 5 kinds of short-circuit faults that can occur on three-phase systems. They are three-phase, line-to-line-to-line faults, or line-to-line-to-line-to-ground faults. Line-to-line faults, double line-to-ground, and single line-to-ground faults. For bolted faults, we combine the sequence networks in the following ways to calculate the fault currents. For three-phase faults, we use the positive sequence network. For line-to-line faults, we use the positive and negative sequence networks connected in parallel. For double line-to-ground faults, we use the positive, negative and zero sequence networks connected in parallel. For single line-to-ground faults, we use the positive, negative and zero sequence networks connected in series. Since the faulted circuit for the bolted three-phase fault, and the bolted three-phase faults to ground, are balanced, we use the positive sequence network. In the symmetrical three-phase to ground fault, ideally, there are no ground or neutral currents. The fault currents are the currents in the phases. For the single-phase to ground fault, the positive, negative and zero sequence networks are connected in series. The zero sequence, positive sequence and negative sequence currents are equal. For double line-to-ground faults, the positive sequence, the negative sequence, and the zero sequence networks are connected in parallel. Therefore, V0, V1, and V2 are equal. For line-to-line faults, the positive and negative sequence networks are connected in parallel. The positive sequence current is equal to minus the negative sequence current, and the positive sequence voltage is equal to the negative sequence voltage. The zero sequence current is zero. For three-phase faults, where the fault has an impedance, the impedance is placed in series with the positive sequence network. The total impedance is Z1 plus ZF. For the line-to-ground impedance fault, the fault impedance is placed in series with the zero sequence, positive sequence and negative sequence impedance. For the double line-to-ground impedance fault, the fault impedance is placed in series with the zero sequence network. Then the combination is placed in parallel with the positive and negative sequence networks. For the line-to-line fault, the fault impedance is placed between the positive and negative sequence network. When we first encounter a subject, we can use methods given by others to solve problems with very little understanding of how those methods were developed. We can use those methods indefinitely without ever exploring their derivation to solve most problems. However, we can do a deeper dive into how the methods were developed to become enlightened. Once we do, we obtain a deeper understanding of the subject. Once we have been enlightened, we go back to just using the methods. However, being enlightened, we can apply the methods to new situations and develop additional methods with confidence. We know that we know. In the following section we will derive the methods of interconnecting sequence networks for fault calculations. Let us define two matrices. The matrix A contains the coefficients of the fundamental equations to convert from the sequence variables V0, V1, and V2 to the phase variables VA, VB, and VC. Likewise for the currents. The matrix A inverse contains the coefficients of the fundamental equations to convert from the phase variables VA, VB, and VC to the sequence variables V0, V1, and V2. Likewise for the currents. The matrix A times A inverse yields the identity matrix. Let us write the fundamental equations in matrix form. The sequence variables are equal to A inverses times the phase variables. The phase variables are equal to A times the sequence variables. These are the calculations of the matrices we will need shortly. Given the network shown, that is not necessarily symmetrical, applying the fundamental equation to the impedances, we get the series self-impedance sequences. Z0 equals 1/3 times the quantity ZA plus ZB plus ZC. Z1 equals 1/3 times the quantity ZA plus A times ZB, plus A squared times ZC. Z2 equals 1/3 times the quantity ZA, plus A squared times ZB, plus A times ZC. Now, let us multiply the diagonal matrix CA, ZB and ZC on the left, by the matrix A inverse, and multiply on the right by matrix A. Now, using the properties of the A operator and substituting the series self-impedance values into the above matrix, we get the series self-impedance matrix. We see that the first element on the diagonal is Z0. Since A cubed is equal to 1, the second and third elements on the diagonal are also equal to Z0. Now, if we examine the off-diagonal elements, we find they are equal to Z1 and Z2 as shown. If the system is balanced, where all the impedances are equal to Z, we see that Z1 and Z2 are equal to Z times the quantity 1 plus A squared, which is equal to 0. Therefore, the off-diagonal elements are 0 when the system is balanced. If the system is unbalanced, the off-diagonal elements are non-zero. Writing the equations for the network in matrix form, we get the matrix equation shown. The matrix equation just says that VA is equal to the source voltage EA minus the voltage drop across CA due to IA. Likewise for VB and VC. We convert the network equations to symmetrical component equations by multiplying the network equation by A inverse and inserting the identity matrix A times A inverse between the impedance matrix and the current vector. Performing the matrix operations, we get the equation shown. The equations below show the interactions between the different sequences for a non-symmetrical network. For the unbalanced network, V0 is influenced by I1 times Z2, plus I2 times Z1, in addition to V0 times Z0. Likewise for V1 and V2. These equations, along with the boundary conditions, show us how to connect the sequence networks for the different types of faults. Usually, we have a circuit drawing and we are trying to find the equations of the circuit. Here we have the equations and are trying to find the circuits that fit them. Let us examine the bolted line to ground fault. The boundary conditions are IB equals 0, IC equals 0, and VA equals 0. Entering the boundary conditions for the phase currents, we calculate the sequence currents. Notice that all the sequence currents are equal. This suggests a series circuit. Substituting the boundary conditions for the phase voltages, and calculating the sequence voltages, we get the equations shown. The sum of the voltages V0 plus V1 plus V2 equals 1/3 the quantity 1 plus A squared times VB plus 1 plus A squared times VC equals 0. Since 1 plus A squared equals 0, this meets the requirements for the sum of the voltages around a closed loop be equal to 0. Substituting the boundary conditions into the circuit equation, we get the results shown. Drawing the circuit. The series circuit shown satisfies the circuit equation and boundary condition of the line to ground fault. However, notice the circuit is not quite the same as previously shown. This is because no assumptions have been made as to the symmetry of the source voltages nor the series impedances. Now let us consider the circuit excited by a balanced three-phase voltage where the series impedance are equal and there is mutual coupling between the phases. The dependent voltage sources model the induced voltage caused by the mutual inductance Xm between phases. That is, the voltage drop in phase C caused by the currents in phase A and phase B. The mutual couplings are assumed to be equal. Calculating the series impedances, including the mutual impedances and substituting into the sequence network equations, the sequence equations are as shown. Since the exciting voltages are balanced, the E0 equals 0 and E2 equals 0, then the network reduces to the network shown. If there is no mutual coupling or the mutual coupling is accounted for in the series impedance, then the circuit becomes. If the line is faulted to ground through an impedance, then the voltage boundary conditions becomes VA equals IA times ZF, with the other boundary conditions remaining the same. Inserting for VA in the matrix equation. Summing the sequence voltages. V0 plus V1 plus V2 equals 1/3 the quantity 1 plus A squared times VB plus 1 plus A squared times VC plus IA times ZF. Since 1 plus A squared equals 0, the sum of the sequence voltages is IA times ZF, and IAZF equals I0 times 3ZF. The voltage boundary condition can be satisfied by inserting an impedance of 3ZF in the series circuit. Let us examine the line-to-line, bolted fault. For the circuit below, the boundary conditions are IB equals minus IC, IA equals 0, and VB equals VC. Inserting the boundary conditions. IA equals 0. IB equals minus IC. VB equals VC. Multiplying gives us I1 equals minus I2. V1 equals V2. V1 equals E1 minus Z times I1. And V2 equals minus Z times I2. V1 equal to V2 suggests a parallel circuit, and V1 is equal to E1 minus Z times I1. V2 is equal to minus Z times I2. Since I0 equals 0, there is no zero sequence circuit. The boundary conditions for the currents are the same. We notice that the voltage boundary conditions are different. IC equals minus IB, IA equals 0, VC equals VB minus IB times ZF. Inserting the voltage boundary condition into the voltage sequence equation, it is not obvious what to do next. As a start, let us determine the current through and the voltage across CF, in terms of the sequence voltages and currents. From the preceding matrices we get the equations shown. Rearranging terms and subtracting the voltage equations, we get 3 times the quantity V1 minus V2 is equal to the quantity A minus A squared times IB times ZF. Substituting the 3I1 from the equation, 3I1 equal to A times IB minus A squared times IB, into the equation for V1 minus V2, we get V1 minus V2 is equal to I1 times ZF. This suggests the circuit shown. For the double line to ground fault, the boundary conditions are VB equals 0, VC equals 0 and IA equals 0. Inserting the boundary conditions, we get the following equations. Multiplying gives us I1 equals minus I2. V1 equals V2. V1 equals E1 minus Z times I1. And V2 equals minus Z times I2. From the previous equations we notice V0 equals V1 equals V2. And V0 equals minus Z times I0. V1 equals E1 minus Z times I1. and V2 equals minus Z times I2. This suggests the circuit shown. Next we look at the double line to ground fault through an impedance. Inserting the boundary conditions, IA equals 0. VB equals VC. VB equals the quantity, IB plus IC, times ZF. We get the following equations. Notice that V1 is equal to V2. Substituting I0 in the voltage equations, we get, subtracting V1 from V0, we get the following results. Substituting the sequence currents into the network equations, simplifying, we get, from the equations, V1 equals V2. V1 equals E1 minus C1. V0 equals minus I0 times C0. V2 equals minus I2 times Z2. V0 minus V1 equals 3 times I0 times ZF. We deduce the network. Next we will solve a transmission network example. Given the network, we will calculate the fault currents for the different types of faults at bus 3. The table gives the per unit positive, negative and zero sequence reactances for the equipment in the transmission system. Use the following rules to draw the positive sequence network. Draw your reference bus first. Connect the negative terminal of your sources to the reference bus. Connect one end of your load to the reference bus. Connect the line and equipment series impedances in accordance with the network topology. Always draw the positive sequence network first. The positive sequence network. Draw your reference bus first. Connect the negative terminal of your sources to the reference bus. Connect the line and equipment series impedances in accordance with the network topology. Use the following rules to draw the negative sequence network. Copy your positive sequence network. Change the name to negative sequence. Remove the voltage sources by shorting them. Change the impedance values of your non-passive equipment, i.e. rotating equipment, if they are not the same as the positive sequence. Copy your positive sequence network. Change the name to negative sequence. Remove the voltage sources by shorting them. Change the impedance values of your non-passive equipment, i.e., rotating equipment, if they are not the same as the positive sequence. Copy the negative sequence network topology. Change the name to the zero sequence network. Copy the transformer phasing connections from the one-line diagram. Modify the impedance drawing per the following. For the solidly grounded Y equipment there is no change. For a delta connection, open the circuit, since there is no path for zero sequence currents. For the ungrounded Y, open the circuit, since there is no path for zero sequence currents. For impedance grounded Y, insert 3 times the neutral impedance in series with the equipment impedance. In the transformer diagram, zero sequence currents flow out of bus B and through the transformer windings. However, zero sequence currents do not flow into bus A. To model this, we open the negative sequence circuit topology between the transformer and bus A. This prevents current flow to bus A. It also prevents current flow from bus B through the transformer windings. Therefore, we must connect the transformer winding to the reference bus to provide that current path. In the transformer diagram, zero sequence currents flow out of bus B, through the transformer high-side windings, then through the high-side neutral impedance ZNH. Zero sequence currents also flow through the low-side neutral impedance ZNL through the low-side winding into bus A. Therefore, we have a path for zero sequence currents from bus B to bus A through the neutral impedances. We insert 3 times the neutral impedances in series with the transformer zero sequence impedances. Copy the negative sequence network topology. Change the name to the zero sequence network. Copy the transformer phasing connections from the one-line diagram. Open the delta connections. Connect the Y connection to the reference bus. Insert 3 times the neutral impedance into the network. This is the resulting zero sequence network. Now, using our network theorems, we calculate the Thevenin's equivalent circuit for the networks. For the positive sequence network, we get a voltage of 1 at 0 degrees per unit, and an impedance of 0.175 per unit. Since the system contains only passive elements except for the sources, and the source's negative sequence impedance equals the source's positive sequence impedance, the negative sequence network is equal to the positive sequence network with the sources removed. Reducing the zero sequence network, we obtain a zero sequence impedance of J0.1989 per unit. For a balanced network, we use the positive sequence network to determine the fault currents. I1 equals E1 divided by Z1. I1 equals 1.0 volts, at 0 degrees divided by 0.175, at 90 degrees. I1 equals 5.714, at minus 90 degrees. We know that IA equals I1, therefore, IA equals I1 equals 5.714, at minus 90 degrees. IB equals 5.714, at minus 90 degrees plus 240 degrees. IC equals 5.714, at minus 90 degrees plus 120 degrees. IA equals 5.714 at minus 90 degrees. IB equals 5.714 at 150 degrees. IC equals 5.714 at 30 degrees. We know from the boundary conditions that VA, VB, and VC equals 0. We can also calculate the faulted circuit's currents and voltages using the transformed network equations and the fundamental equations. Calculating the sequence currents. The positive sequence current is E1 divided by Z0. The zero and negative sequence currents are zero in a balanced three-phase fault. Using the fundamental equations, we can calculate the phase currents IA, IB, and IC. Entering the sequence currents into the network sequence equations, we can calculate the sequence voltages. Then using the fundamental equations, we can calculate the phase voltages. In the case of the bolted three-phase fault, the phase voltages are zero. For the single line to ground fault, all the sequence currents are equal. The sequence current is E1 divided by the sum of the sequence impedances. Substituting the sequence currents into the fundamental equations gives us the phase currents. Entering the sequence currents into the network equations, we calculate the sequence voltages. Entering the sequence voltages into the fundamental equation, we get the phase voltages. Notice the 2.3% voltage rise on the unfaulted phases. In a Y-connected network, you have two load elements connected across two phases. In the drawing, ZA and ZC are connected across VA and VC. If we have a line to neutral fault, ZC is shorted out. If the Y circuit is ungrounded, this puts VA plus VB across the single element ZA. This will put a voltage of 1.73 per unit across an element designed for 1.0 per unit voltage. If the Y circuit is solidly grounded, VC will be shorted to ground, therefore the voltage across ZA will remain at 1 per unit. Depending on the value of Zn, the voltage rise can vary from 1 per unit to 1.73 per unit. This holds true for the other unfaulted phases. For the line-to-line fault, we connect the positive sequence network in parallel with the negative sequence network. This gives us the network shown. I1 is equal to E1 divided by Z1 plus Z2. I2 is equal to minus I1 and I0 is equal to 0. Using the same procedure, we substitute the sequence currents into the fundamental equations to get the phase currents. We then enter the sequence currents into the sequence network equations to get the sequence voltages. Substituting the sequence voltages into the fundamental equations, we get the phase voltages. For a double line to ground fault, the positive sequence, negative sequence and zero sequence circuits are connected in parallel to get the circuit shown. We use the network theorems to calculate the sequence currents, and as before, we enter them into the fundamental equations to get the phase currents. We again enter the sequence currents into the network equations to get the sequence voltages. We then enter the sequence voltages into the fundamental equations to get the phase voltages. In the previous examples we have made certain implicit assumptions. In neglecting the resistance we have assumed the reactance is much greater than the resistance. This was done to simplify the calculations, however in computer studies this is unnecessary. We have neglected the load currents, assuming that the fault currents are much greater than the load currents. This is not always true. The load currents and voltages can be accounted for by solving the pre-fault circuit, load flow, and using superposition to combine the pre-fault and post-fault circuits. We have assumed that the generator voltages are in phase, which is generally valid for unloaded circuits. We have assumed that the circuits are linear and their constants are time invariant. We have considered only the steady-state voltages and currents. There are transient conditions that need to be examined. In compiling this video, the following references were used.